Welcome to AI Paper Podcasts, where we break down the latest research so you don't have to.
Today, we're digging into a really significant paper from Stability AI, SD3.5 Flash, Distribution Guided Distillation of Generative Flows.
Yeah, this one promises to tackle a major bottleneck, getting top-tier image generation models out of the data center.
Exactly. Right now, the best models, especially these rectified flow ones, they're just too demanding. We're talking, 25 plus steps?
And needing like 16 gigs of VRAM, taking maybe 30 seconds or more per image. Basically not something you can run easily.
Definitely not on your laptop, little on your phone. So this paper, SD3.5 Flash, aims to change that.
Right, bringing that quality down to consumer devices. Okay, so for the quick summary, the TLDR for everyone.
So SD3.5 Flash is this super efficient distillation framework. It's high quality in just a few steps by fixing key problems in flow distillation.
And the core ideas, there were three main technical bits, right?
Yeah. First, time step sharing. This helps stabilize the training gradients, which is crucial when you only have a few steps to work with.
Okay, and second?
Second, split time step fine-tuning. It's a clever way to temporarily boost the model's capacity during training to get better prompt alignment without sacrificing image quality.
Gotcha. And the third piece was more on the engineering side.
Right. Comprehensive pipeline optimizations. This means things like restructuring the text encoders, getting rid of the massive T5XXL, and using aggressive quantization, down to 6-bit even.
Wow, 6-bit. And the result of all this?
A set of models that apparently beat existing few-step methods and user tests and, get this, offer up to an 18x speedup compared to the original big teacher model, SD3.5M.
18 times faster, that's huge. Okay, let's really dig in. Section 1, the distillation challenge. Start with that accessibility gap.
So the teacher model they're distilling from, SD3.5M, it runs at 50 steps.
50, and needs nearly 20 gigabytes of VRAM.
Yeah, 19.47 giga, technically. That absolutely requires high-end server GPUs. Your average user, even a developer with a decent machine, might struggle.
And this isn't unique to SD3.5M, right? It's typical for these high-quality rectified flow models.
It is. Rectified flows are great because they learn these smooth, straight paths from noise to image. That smoothness equals quality. But compressing that 50-step path down to, say, 4 or 6 steps, that's where things get really tricky.
So why does the standard approach, distribution matching distillation, or DMD, why does it fall apart here?
Well, standard DMD involves comparing distributions. It takes the student's generated image, the $6 dollars, and adds noise back to get to some intermediate time dollars.
Okay.
Then it compares the student's prediction at that $6 to the teacher's. The problem is, when you only have a few steps, like 4, that renoising step, it massively destabilizes things.
How so?
You're essentially injecting artificial noise, which wasn't part of the student's actual path from the initial noise to the final image in those few steps. This corrupts the gradient signal the student uses to learn.
Ah, okay. So the signal it's learning from is wrong, or at least not representative of the actual few-step path it needs to learn.
Exactly. And because it only has a few steps, it can't easily correct errors introduced by this noisy signal. Unlike a 50-step model, which can refine things over many iterations.
The paper calls it systematic quality collapse, right?
That's the term, yeah. The model just can't handle the noisy updates from standard DMD in this low-step regime. It's like trying to follow complex directions with only 4 checkpoints. One wrong turn early on throws everything off.
Makes sense. And beyond just stability, there's this trade-off between quality and following the prompt, semantic fidelity.
Right, the capacity constraint problem. When you dramatically shrink a model, forcing it into fewer steps, it often has to choose. Does it make a pretty picture, or does it accurately represent a complex prompt, like a red cube sitting on a blue sphere under a green light?
And usually it prioritizes just making it look good, visually appealing, over getting all the details of the prompt right.
Often, yes. Especially because getting that detailed prompt understanding usually relies on those really big text encoders.
Like the T5XXL you mentioned earlier, which is exactly what they want to get rid of for efficiency.
Precisely. T5XXL is amazing for understanding nuance, but it's a memory beast. So SD3.5 Flash needed new algorithmic tricks to maintain prompt fidelity without relying on that huge encoder while also solving the stability problem.
Okay, let's move into those solutions. Section 2, the algorithmic innovations. They started with something before the main distillation, this LTG trajectory guidance pre-training.
Yeah, think of it as laying the groundwork. Before they even start the tricky distribution matching, they pre-trained the student model just to copy the teacher model's velocity.
The velocity predictor, why that specifically?
Because the velocity defines the direction and speed of the flow, basically, the path from noise to image. But importantly, they only make the student match the teacher's velocity at the specific time steps the student will actually use.
Ah, so not all 50 steps, just the, say, 4 or 6 points the student model will hit.
Exactly. It gives the student a basic sense of the correct trajectory, aligns it roughly with the teacher, making the next harder stage of training faster and more stable. It's like sketching the route before adding all the details.
Okay, foundation laid. Now, the core fix for the stability issue, time step sharing. How does this get around the noisy gradient problem of standard DMD?
It's quite elegant, actually. Remember how standard DMD takes the final image, $6, and adds noise back?
Yeah, which causes the problems.
Time step sharing avoids that completely. Instead of generating a noisy $6 from the final $6, it uses samples directly from the student's current ongoing trajectory.
So it grabs one of the intermediate steps the student is already producing in its, say, 4-step process, like 6.
Precisely. It uses these partially denoised samples from within the student's own flow generation. Because 6MLTs is a known point on the current path the student is taking, particularly the next step from there is much more reliable.
And the gradient you calculate from that is much cleaner, much more stable.
Exactly right. You're optimizing based on the model's actual current state and trajectory, not some artificially noised up version of its endpoint.
That makes a lot of sense. It avoids compounding errors from bad $6 estimates, especially at the very noisy beginning stages.
The paper's ablation study showed this was critical. Removing time step sharing really hurt the results. Bad textures, weird colors, messed up compositions.
Okay, stable gradients achieved. But we still have the prompt alignment challenge, the semantic fidelity issue, especially after ditching big encoders. This brings us to split time step fine-tuning. This sounds complex, temporarily increasing capacity.
It is a bit more involved, but it directly targets that trade-off. Few step models struggle to capture all the prompt details, so during the second training stage, after the initial LTG pre-training, they do something interesting. They duplicate the student model.
Duplicate it, so 2 copies.
Yep, 2 branches, $100 and $2. Temporarily doubles the parameters they're training, but they train each branch differently. gets trained only on the later, less noisy time steps. Say, T devolves between 0 and 500. It focuses on refining the details, sharpness, textures, the stuff close to the final image.
Okay, the finishing touches model.
Sort of. And $2 gets trained on the earlier, noisier time steps, maybe between 500 and 1,000. This branch learns the big picture stuff, the overall composition, the structure, and crucially, how to interpret the prompt context.
Ah, so $1 is about how it looks and tells about what it is and where things go.
That's a good way to put it. One handles fine details, the other handles course structure and semantics.
Then what? You can't deploy 2 models. How do they combine them?
After both $4 and $2 are trained, they merge them back into one model using weight interpolation. They literally average the weights of the 2 branches.
Just average them, or is there a specific ratio?
They found a specific ratio worked best. They weighted TEMDIOR, the course structure semantics branch, more heavily, a 3-to-7 ratio, $10 to $10. This specific blend gave the best scores on GenEval, which measures how well the image matches the text prompt.
Interesting. So temporarily specializing parts of the model and then blending them lets the final single model inherit the strengths of both, boosting that prompt adherence significantly for the few-step version.
Exactly. It resolves that capacity tension without needing a permanently larger model at inference time.
Very clever. And quickly, they also used an adversarial loss, right, like in some other distillation work.
They did. Similar to things like nitrofusion or DMD2, they added a Jan component. It operates in the latent space of the flow model. The student model's predictions are judged by discriminators.
Anything novel there?
One key detail for stability was that they periodically reinitialized the discriminator weights. This stops the discriminator getting too good and overfitting, which can actually derail the whole training process. It keeps the adversarial pressure helpful, but not destructive.
Right. Classic Jan training instability. Okay, let's get to the payoff. Section 3. Performance and democratization. This is the flash part. The algorithms are cool, but making it run fast and light is key.
Absolutely. The big target here was VRAM. We mentioned the original SD 3.5 pipeline had 3 text encoders, CLEP Lite BCL, CLEP-G, and that monster T5XXL.
And T5XXL was the main problem for memory and speed.
The paper explicitly states it accounts for the bulk of peak VRAM usage and inference time. So it had to go if they wanted this running on phones and laptops.
How do they compensate for losing all that semantic power from T5XXL?
They used a technique called encoder dropout pre-training. Essentially, the model was already trained to sometimes cope without the T5XXL input during its earlier development. So at inference time, they can just feed it null embeddings instead of the T5XXL output.
So it learned to manage without it sometimes.
Kind of, yeah. And then critically, they applied aggressive quantization to the main image generation model, the MMDIT.
Quantization meaning using fewer bits to represent the model's weights.
Exactly. They showed results going from the standard 16-bit model, which still needed 18 GIBs even after distillation, down to an 8-bit version. Without T5XXL and quantized to 8-bit, the memory requirement dropped to just 8 GB.
That's a huge drop, from nearly 20 down to 8. But they went further.
They did. For edge devices like iPhones and iPads using Apple's CoreML framework, they pushed it down to 6-bit precision.
6 bits. And the performance numbers there were pretty wild.
Seriously impressive. A 4-step generation at 512 x 512 resolution using the 6-bit model. 2.62 seconds on an M4 iPad.
2.5 seconds on an iPad.
And 3.25 seconds on an A17 iPhone. Think about that. High-quality AI image generation, basically instant, on the phone in your pocket.
That really does change what's possible for mobile apps. And the user studies backed up the quality.
They did. Across different hardware server GPUs, laptops, mobile users consistently prefer the SD3.5 flash models over competitors like SWDM, SDXL HyperSD, and SDXL Lightning when comparing models running similar few steps.
But the most surprising thing was comparing it back to its own teacher, right?
This was the kicker. In large user studies with over 120 people rating images from over 500 prompts, the 4-step SD3.5 flash model was rated as having higher overall image quality than the original 50-step SD3.5M teacher model it was distilled from.
Hang on. The compressed 4-step student beat the full 50-step teacher on aesthetics. How does that even work?
It's counterintuitive, I know.
Yeah.
The human preference scores, using metrics like image reward, consistently favored the 4-step flash model for visual quality. Prompt adherence was roughly similar, maybe marginally different depending on the models compared, but for just pure image quality, the student pulled ahead.
Wow. Maybe less is more sometimes.
Perhaps. The paper suggests it excels where other few-step models often fall down, things like getting anatomy right, handling compositions with multiple objects cleanly.
But they do acknowledge the trade-off from removing T5XXL, right? It's not all upside.
Oh yeah, they're clear about that. Removing T5XXL, while essential for speed and memory, does make it harder for the model to handle really complex, nuanced prompts that require intricate understanding of spatial relationships or abstract concepts. You lose some of that deep conditional context.
So there's still that tension between speed, size, and maximum semantic complexity.
Definitely. It's the fundamental engineering challenge.
Okay, let's synthesize this. What's the big takeaway for the AI researchers and engineers listening?
I mean, the immediate impact is huge. You no longer necessarily need a cluster of A100s to develop, test, and deploy really high-quality image generation. Prototyping on your laptop, deploying to edge devices, this becomes much more feasible.
It dramatically lowers the barrier to entry and raises the ceiling for what edge AI can do.
Absolutely. It makes high-fidelity generative AI potentially a commodity, accessible everywhere.
Which brings us to our final thought. You mentioned those user studies deliberately separated judging image quality from judging prompt adherence.
Right, there were distinct evaluations.
And the 4-step student beat the 50-step teacher on pure aesthetics, on human preference for the image itself. It makes you wonder.
What are you thinking?
Well, could it be that the intense pressure of distillation, the constraint of having only 4 steps, actually forced the student model to find a more efficient, maybe even more aesthetically pleasing path from noise to image? A path the original 50-step teacher, with all its freedom, never quite settled on.
That's a fascinating idea. Like the constraints themselves led to a kind of emergent optimization towards what humans find visually appealing, maybe pruning away trajectories a teacher might explore that lead to less pleasing results.
Exactly. If the goal is just to replicate the teacher, you might copy its flaws or inefficiencies. But if the distillation process, perhaps unintentionally here, results in something humans prefer, what if we start designing distillation objectives that don't just aim to match the teacher, but to actively surpass it based on human preference metrics?
Focusing distillation not just on mimicry, but on optimization towards a human-defined aesthetic target, even within those few steps. That could lead to entirely new kinds of generative models.
Something to think about next time you're generating images in seconds on your device.
Definitely food for thought. Thanks for tuning in to AI Paper Podcast.
We'll catch you on the next one.